Greetings, Attorney Santos A. Perez of the Perez Law Firm, njlawcounsel.com. The purpose of this video is basically to set forth my qualifications to comment on the Stability AI class action lawsuit. Now, I do have a pretty comprehensive background in computer science. I have an advanced degree from Rutgers University, but it goes back over 2 decades. So during the pandemic, what I did is I enrolled in the University of Texas. It's a competitive program. I got in on merit. And their master's program in computer science for artificial intelligence. I was admitted and I immediately took 2 grueling courses that I had no idea were this difficult. The machine learning course was more theoretical, but it also had the more advanced mathematics. I also took a deep learning course, which basically focuses on the neural network or the deep neural network, which is excruciatingly difficult to understand. But once you do, you get it. The deep neural networks are general purpose machines or constructs, which you can use for a variety of tasks, including computer vision, generative models such as Stability AI, generative models such as ChatGPT or Bard. Let's get into the heart of what I did at the University of Texas. This is actually a Google Colab notebook. They're also known as Jupyter notebooks, but it's a notebook that allows me to code in any particular language, in this case, Python or PyTorch, and I can use Google's immense supercomputing power to work on my projects. And in this case, a neural network can process hundreds of thousands of images per second, so that I needed pretty formidable computing power, and Google was the answer, and that's what I did. This is very simple. This code right here loads the code from my GitHub repository into Google Colab. As you can see here, I gave it previously my name as well as the password. And then this loads the code so that then I can run it in Google's supercomputers. And this code right here, basically what it does, it loads an API, an application programming interface, to a go-kart simulator, which simulates a go-kart and allows you to play games. This is where I upload, or where I obtained my data from in order to train my neural network to recognize objects on the ice hockey field. This is where that API is loaded. And again, I use this, A, to extract images to train my network, and B, to test my network after I've trained it. Now let's go back to my GitHub repository. Let me go a few directories up here. Deep Learning Masters class. As you can see here, there are a number of projects that I did as part of my deep learning class, and including right here where it says extra. I designed a temporal convolutional network, which is basically a generative AI model similar to Stability AI, a lot less complex. It's basically an autocomplete system which guesses or predicts the next letter in a sentence. That's all it does. But that is autocomplete, is in fact generative AI. Then we get here, this directory takes me to the final. As part of the final, we had to design the computer science or the computer vision model to allow a go-kart to drive around a hockey field. There were 4 people in my group. We subdivided the group into 2 groups of 2 each. My partner dropped out. She could not handle the final. She dropped out of the course. So I was on my own. I opted to go with what's called an image agent. My colleagues decided to go with what's called a state agent, using reinforcement learning. At the end of the project, because they did not get their reinforcement learning state-based approach to work, they opted to go with mine. Now let's click here on image agent, and that'll take us to my version of the project, the image based. It's comprised of a number of PyTorch or Python files Let's begin with the planner.py file. Let me click on that. This file basically defines the structure of the neural network and also defines a function which allows me or allows the programmer to feed images into the network and to obtain an output. And the output will be the X and Y coordinates of the hockey puck. The purpose of my image-based agent was basically to teach a go-kart to recognize an image and find the hockey puck on the image and determine where that hockey puck is. Depending on where the hockey puck is, the go-kart will drive to the left or to the right or go straight, so that the XY coordinates of the hockey puck were pretty significant, and that's what my network did. What we first do is basically define the network itself in an object. This is object-oriented programming. This is object-oriented programming, and there's something called an init function, which is called the constructor, which is called when you first declare the variable in your code. In this case, we're going to declare the variable in the train.py module, which you'll see later. And so when we invoke or we declare this object, the constructor is called, and it basically builds in the computer's memory. It builds the neural network with these specs right here. It's a convolutional neural network used for computer graphics with these specs that you see here, which define basically the number of levels of the neural network, the number of nodes that it has, and other aspects of the network. Going down further, this code continues to define that. There are tons of different ways, even though some of this code is boilerplate, or the idea is boilerplate. Tweaking around with these parameters to change the size and structure of the network does take some knowledge. You have to have some ability, and you have to know why you need to make some changes. So that's what this code does. This entire code here, it creates the structure of the neural network. This method within the planner object, which is the neural network, is what allows me to pass it. If you see here something called image, it's an argument that is passed to this method, and you pass an image to the method, and it will run the entire image through the network, and then it will come up with an answer, with an output in the form of XY coordinates. So what the image will tell you, or what the network will tell you, is, okay, I've looked at the image, and these are the Y, X coordinate. If the puck is there, because we don't know that it is there in that image, if the puck is there, these are the X and Y coordinates. This will allow me, or the programmer, to let the go-kart know that it has to turn left or right, because generally what it has to do is follow that puck. That was the idea of my computer vision model. Initially, this network that I created, or any new network, is ignorant. It knows nothing. And so the output will be gibberish. It'll tell you initially, when you pass an image the first time, or every image in the data set. In this case, there were probably about 100,000 images that I extracted from the simulator. When you pass each one of these images through the network, it's going to give you XY coordinates that make no sense. My job, the job of the programmer, is to teach this network how to give me the correct XY coordinates, so that if the puck is, let's say, is to the right of the image, it should give you the coordinates that depict that location. If it gives you coordinates that depict the puck in the upper left quadrant, for example, of the image, that would be incorrect, and we have to teach the network to get it right. That's the purpose of programming the neural network and teaching it. This is why this is called also called data science, because we're learning from images. And remember, when I extracted these images, and I'm going to go over that now. When I extracted these images, I also extracted from the simulator, I also extracted the XY coordinates of the puck in that image And by the way, this is a part of the project that I did on my own because my teammate dropped out. I was on my own. I had two other teammates, but they were working on a reinforcement model state-based approach, which ultimately did not work. So I did this completely on my own, extracting the images and obtaining the labels, the XY labels. So what do we do with these labels? And my network is ignorant. It doesn't know how to do anything, but I have the labels. Can I teach my network how to do this correctly? Well, yes, I can. Train.py, some of the code here is in fact boilerplate, but it takes skill in tweaking with the hyperparameters. And you really have to understand what's going on. And I did. So we had to work with the parameters and juggle some things around. And there are other ways to accomplish the same purpose. This is just one boilerplate version. So we go here, first code that stands out, model equals planner. This is the definition of the object, a planner. So we call the class, we let the computer know that we're defining a new structure, a new neural network, which is going to be defined according to the planner class that I designed in the other file, the planner.py file. That creates the neural network essentially. So now it's in memory, but it doesn't know how to do anything. Then we come down here. For epoch, in range, rh.number of epochs. So we're going to run, epoch could be any number from 10 to 1,000. What that means is that we're going to run through the entire data set. In my case, I believe I had extracted about 100,000 or more images. We're going to go through that entire data set between 10 to 1,000 or more times to teach my network to get it right, because it's going to continue making mistakes. Now, there's something called overfitting, and one thing that programmers have to know, or machine learning or deep learning enthusiasts or programmers have to know, is that if you define epoch as having too high, let's say you do it you do 10,000 epochs, so that the computer or the model is trained on your data set 10,000 times. Essentially, after 10,000 times or 10,000 iterations through the entire data set of over 100,000 images, it's going to learn. It's going to know what in each image, it's going to know where the puck is and whether it has to turn left or right, what the coordinates are. It's going to learn that. But you have to learn how to avoid a common problem called overfitting. If the model learns each image to perfection, chances are that if you give it a new image with the hockey puck at a location that was not part of its training data, that it's not going to get it right. It's not going to get it right because it overfitted. It knows the entire data set by heart, but it doesn't know how to generalize. So it'll give you wrong coordinates for any new images, and it only knows the images that it was taught on. So bottom line, the number of epochs is a key variable. It has to be controlled, and to avoid overfitting, so that the model knows how to generalize well. It learns the data that it was given, so that it knows how to identify the XY coordinates of the puck in each one of the pictures, but it doesn't do it to perfection, so that it knows how to, it's got a little bit of flexibility. And if you give it a new data set, new pictures, extracted from video, obviously, it'll be able to give you the correct XY coordinates. So here we go. Here for image label and train data, this basically means we go through the entire data set. If it's 100,000 images, then 100,000 images. If it's 1,000,000, then 1,000,000. And we obtain various specs from these images. This is the height and the width. Here, what I'm doing is I'm making a prediction. So I'm getting the XY coordinates of the puck in the first image. The first time around, it's going to be the first image. Then we go through the 100,000 images, and we obtain the predicted value, the XY, the prediction, the XY values or coordinates of the hockey puck for each one of the images. First time around, this is going to be wrong. It's not going to make any sense. If the hockey puck is at the upper right quadrant, it'll give you coordinates which depict a lower left quadrant, something along those lines. It may get it right by luck, but generally it's going to be wrong. So we have to train it. How do we train it? Well, we get here xy equals label.chunk. What I'm doing basically is I'm obtaining the right coordinates so that I have an image. I had extracted previously, remember, the labels for these images, so I know what the xy coordinates of the puck are. If my network got it wrong, then I can see it now, or the computer program can see it. So we extract the correct values. So now we have xy, which are the correct values, xy coordinates of the hockey puck. Then we have the prediction, which is the predicted xy coordinates. Now we have to just get it right. We have to make sure that they're right. They're going to be wrong. So knowing that, we conclude or we compute how wrong they are. Loss value equals loss prediction comma xy. What this is a function call. Loss is actually an object. That's a different subject, object-oriented programming. So it's calling a method. But anyway, loss basically decides how wrong my prediction is. So I came up with a set of predictions. It's going to be wrong the first time. So how wrong am I? And that value is going to be stored in loss value. Now I know how wrong I am. So how do I fix that? The way this is done is that you go back to the network and you tweak around with the parameters, called actually the weights of the neural network, so that the neural network computes the right XY values. It got it wrong, presumably, most likely. So now it's going to go back and it's going to update its weights, and so in such a way so that it computes the right XY coordinates given that particular image. And then here's the beauty, here's the key, loss val dot backward. That's where it actually goes back through the neural network. It does back propagation, updating the weights so that the correct calculation is made based on that one image, so that you arrive at the right XY coordinates at the end. And then you do a little bit more housekeeping here, optimize that step, global step, and then you get the next image in the data set, and you do that for each and every image, and eventually your network will learn will know for each image in that data set where the hockey puck is or what the XY coordinates are. Again, we have to work with the number of epochs to make sure that it doesn't learn it to perfection, because if it knows the exact coordinate for each one of my 100,000 images, then chances are that if I feed it a new image that's not in that data set, it's not going to get it right. Or it's not probable, but it can happen. So that's part of what we learn how to avoid. That's a big aspect of artificial intelligence or deep learning. So that's how this entire process works. Let's do a stop sharing here. So there you have it. This is my training, and sorry if I did not explain it properly, but I did design this, and so that I hope that you're satisfied that I can comment on the Stability AI class action, and I will be doing so. At this point, I believe the class action lacks some merit, but we'll see how that changes. It could be that once I look at the corpus, the data set used to train Stability AI, maybe I'll have a change of heart. At this time, as I said previously, Stability AI does not aim to predict or does not aim to generate any particular image. What it does instead is it aims to generate an image which comports with multiple images that it learned from, not just one. It learned from multiple images, and it's going to give you a result that learns from that comports with all of them, meaning that it's not going to reproduce any particular copyrighted work. More on that in a subsequent video. Complex civil litigation, complex criminal litigation, njlawcounsel.com, 201-875-2266. Thank you.